mass is. Then we'll calculate the center of mass of a specific system, and we'll discuss a relationship between the center of mass and torque. We'll analyze a problem using center of mass and torques. The center of mass is a weighted sum. Here we have a definition for the center of mass of a discrete set of point masses. First thing we do is choose a reference point with which to measure our xi's. Then we take the sum of our incremental masses and their positions over the sum of the masses. We can sort off the sum of masses and call that capital M the total mass. Then we're just saying that the center of mass equals 1 over m times m1x1 plus m2x2 plus all of the points in between up to mnxn. As we've shown in the diagram below, the masses are at discrete points and they have discrete distances away from some origin or reference point. If we have a continuous mass distribution, we can define the center of mass by taking an integral over the mass. So it turns into x center of mass equals the limit as delta m goes to 0 times of 1 over total mass times the integral of x dm. Center of mass may not even lie inside the object. An object like this has a center of mass that isn't even inside the object. An unconstrained object rotates about its center of mass. So if I throw something through the air and it's spinning as it's flying through the air, that axis of rotation will be its center of mass. An object or a system balances at its center of mass. Here we have a fulcrum with two masses on either side. The right mass is more massive than the block on the left, and so we can see that that block is closer in toward the center. What we have here is the torque is the same side on either side of the fulcrum, not the mass. We'll work a problem like this a little bit later. Let's do an example problem where we're going to find the center of mass of this system of identical constant density blocks, each of mass m. We'll use our method of starting with a diagram and assumptions, known and unknown variables. We'll then write the general equations and specify them for our system. We'll solve symbolically in terms of given variables and do an analysis on a result. Here we know the masses and the positions, and we want the center of mass. We start with our general equation, x center of mass equals 1 over the total mass times the weighted sum m1x1 plus m2x2, etc. Let's do another example problem. Here we have a uniform plank of mass m balancing on a fulcrum. We put a small block of mass m1 near the left end of the plank at distance x1 from the fulcrum. The question is, where would you place a block with a larger mass m2 such that the system was balanced? We'll use our same method of solution. Our known variables are the two masses and the mass of the plank and the distance x1, and we want the distance x2. We're going to drop our mass 2 block and define x2 as being a distance away from the fulcrum. Now what we said was that a system balances where the torques are the same on either side of a fulcrum. A torque is defined as r cross F, where r is the distance from a pivot point and F is the force. We can write the magnitude of torque as Rf sine theta. Here we have two gravitational forces pulling down on our masses, actually normal forces pushing against the plank, and the angle between these two forces is 90 degrees. So for this simple situation, sine theta goes to 1. So for our system, we have torque 1 equals torque 2. Our torque 1 is m1g x1 sine 90. Our torque 2 is m2g x2 sine 90. Our g's and sine 90s cancel, so we have m1 x1 equals m2 x2. Solving for x2, we get m1 over m2 times x1 equals x2. We notice that our units are going to work out because the units of mass cancel. The main points here are that the center of mass is a weighted sum. We can define it for a discrete set of point masses or a continuous mass distribution. We can define it in 3 dimensions, but we've really only worked in 1 dimension in this video. The center of mass may lie outside an object. An unconstrained object rotates about its center of mass. An object or system balances at its center of mass. And there we have the same torque on either side of a fulcrum, not the same amount of mass. That's all we have for this center of mass discussion, so thank you for coming. Please come again soon.